Hello, happy to see you again. So, like the data is not only just extra information. Actually, it's an important tool to monitoring the opportunity that maybe the company needs to focus. So, in this case, we are talking about that there are businesses that have a trillion of rows. I am talking about petabytes. And imagine that if you are trying to search in through these millions of records, how is possible that you can get the data or the answer of this kind of query, right, in less than 1 second? So today in this video, I was explaining what is the secret about that. Like I show you in this diagram, actually it's composed with multiple third-party services that work together to finally to support this massive number of great records and support an incredibly fast to read the data. And we will try to compare why actually if you are trying to do a transactional process to support this kind of data, it will fail. With that comparison, you will know why analytical architecture flow is very efficient to have a data warehouse. Okay, so all this information coming from the book of the same data intensive application book. This is the 2026 edition. Thank you again for watching this video, and okay, we can start it. Okay, maybe we can start defining what is a structure that maybe we can expect on the storage of the for the analyst team. Okay, so in this case we are talking about the star schema. Okay, this is the regular structure that we can expect it. Okay, the idea is to have a fact table and multiple dimensions. So take in mind that, okay, there will be a single fact table that will have a huge number of columns, foreign keys with multiple dimensions. But any dimension it will be refers in any other dimension. It's like only all the dimension it will have a relationship with a fact table. So it will generate like an star. So for that is the reason that is called a star, because there will be a single table and all the dimension it will be related with this fact table. And this fact table it will have 100 of columns because it will trying to support multiple aggregation queries that will be used by the analyst team. So that is the main challenge that you have to handle it in the storage to writing data, read data, and we need to be efficient um, to support these queries. Okay, so that is so. Imagine that if you want to support this kind of table with a regular SQL or regular storage that you have on the Postgres or relational model. Okay, so in this case, this is row-based storage. So imagine. So in this case, I have an example. We have a table with multiple columns. We have an IDs, names, departments, and salaries, right? And you're trying to get a summary of the salary. That's all. So in your mind, maybe you can think that, okay, internally under the hood, when you run this query, first it will read only the salary because you are getting only the total salary, and finally get the sum of all of them, right? And that's fine. But the problem is, first, you have a huge number, you have 100 of columns, and then there are trillions of rows, right? So internally, in the case of on the hard drive or the engine or the process when it's trying to do this query, it's not like you imagine. It's like first when find the index that is located this row, because first there is anywhere here, or you are trying to get all the employees. So the problem it will be that you need to read all the rows that you have in this table or in this fact table, right? So in the disk, actually, you don't store the data, you don't store the row by columns. So in this case, you store the row like a single row with all the columns that have this row. So this row can have 100 of columns, take a mind. So when you're trying to read all the rows and you load that in the memory, you will first load all the rows, all the columns, and then the process it will try to find where is located the column that you want to sum. So that not efficient because you are loaded data that you don't use it, and that is coming with the other column that you don't need to sum. So that is the main problem that you will have with row-based storage. So with that problem, the solution coming with the column-based storage, and the idea coming with the instead to store all the row in the file system or on the disk, you will store only the values that have this column. For example, you will have multiple column storage, right? And for each column, you will store all the values of this column. And each index of this long array of values, it will be the row, right? So you can imagine that the first value of the column ID, it will be of the first value of the column name, for example. So you can assume that the ID one is it have the name Alice, and Alice has the department sales and has the salary. So you can see the advantage of this kind of storage, because if you want to sum the salary, you don't need to load anything about the IDs, names, or department. You only need to load all the values of the salary, and then you have to sum them. So for that reason, actually it will be efficient than if you trying to read a column that you don't need it. So that is the column-based storage. Actually, that is the idea, right? So the next thing is that the advantage of a store with column storage, actually coming with that data compression, because if you have a column that could have trillions of rows, right? We are talking about data warehouses of analytical, okay? So obviously the possibility of the types that could have in this column, it will be limited, right? And actually it will be less than the number of rows that could have this column. For example, if you have the column departments, obviously departments have a limited number of departments in your company, imagine, and obviously the number of rows could be trillions of data, right? So there will be repeated value in multiple times. In this case, we are talking about only salary. In this example, I'm talking about salary, and there is a possibility that multiple people have the same salary, right? So instead to store in the file system in the storage all the 500, 500, 500, 600, 5,000, 5,000, 5,000, 6,000. So instead to store duplicated data, you can compress it to generate a key of each value that you have in this column. So you can have, for example, salary. You can store the key 5,000, and the next of the value of the salary. So if you're trying to, for example, you want to know if the first row have 1,000 of salary, you can generate this bitmap, right? The bitmap is composed that each element, the first element, have this 5,000 salary. You will write the value like a 1. If the second row have the same salary, you will write 1. Okay, and when it's not have this salary, you will write like with 0. So with this approach, actually, you can compose multiple values, unique values of this column, and you generate a bitmap. And with this bitmap, it will finally, if you trying to compare, or you want to if you want to merge everything, finally it will be generate the same. So finally, if you trying to merge all the bitmap that have this this salary column, it will generate the same list of value that we have in the real data, only using the bitmap, right? And and that is the first compression using the bitmap. And the next compression it will be is why actually you need to store 111,000 if there is only a two kind of data, one of zero. So in this case, we will use the round length encoding, load length encoding, and round length encoding coming with the with this pattern. Okay, you have to first try to write with this pattern. You only write how many zero and how many ones, the sequence of the number of zeros and the sequence of the idea is coming with the write the sequence of zeros and one of this salary. Instead to store 111,000 infinite, you only store, okay, first, we started with zeros. How many zeros there are in salary 5,000? There are zero. So there are zero. So you can assume that the first row have something. How many ones have this, the first sequence, the first sequence of salary 5,000? It will be 3. Okay, 3. So you can assume, okay, there are the first 3 rows will have the salary 5,000. And the next, it will be the same. 4, it means how many zeros coming from of these three rows. It will be 4. So there will be 4 that doesn't have this 5,000 salary. And that's all. So with that compression, you can actually generate the bitmap. And with the bitmap, you can generate the column values. So that is the compression that have in this column storage based. Okay, it's the advantage to support trillion of rows, and you don't need to store all the values in multiple times. And actually, another advantage if you're trying to store sorting data, because if you sort the data, you only can the round length encoding, it will be two values, because you only need to count how many zeros there are after appears, how many zeros there are before to appear the first one, and then you have to count how many one there are in the table, and obviously it will be obviously all the ones it will be together, so you need to store only two values there. So that is the advantage when you are trying to sort it. But the problem coming from is how you can handle this massive number of records when you're trying to write in and read it and read at the same time. Okay, so with that problem, we are using the long structure approach that I explained before in the last video. You can see it. You can see it if you want it. Okay, but the idea is coming from that when you receive the data of the ETL, okay, that is the extract, transform, and load the data, right? First coming the data from there, and then it will be loaded in the memory, and the RAM memory, right? Because it will be faster, right? And you need to store them, and first you are trying to accumulate a number of rows there, and when you have a size there, you will finally store it in the object storage disk. Okay, so in this case, in the memory store, it will be the format of the row oriented, because we are not talking about trillions of rows. Obviously, it will be less of that, and it's a temporal process before to be persisted on the object storage. Okay, on the object storage, obviously it will be the format of the column encoding files. Okay, and that's all. So the next thing it will be the next step it will be with the data catalog. The data catalog it actually have the have the responsibility to the governance the data and defining in which places is located the data to be provided for the query engine. Okay, and when the query engine wants to get something, first need to know in which place is located this information, and that in the object storage. So for that reason, the query engines first ask where is that where is the data of my query, and then read the disk of the object storage, and then try to read the recent writes in the memory and generate the order or generate the structure to finally send it to the analyst response. So that is the flow of when you're trying to write something in the analytical architecture flow, right? And this coming with the next challenge of this flow, it will be in the query engine. The query engine needs to be efficient to handle complex query, analytical complex query that affects maybe multiple columns, multiple calculations. So we need to optimize that. And actually, there are two optimizations that you can use in the query engine. First, we are talking about the query compilation. And that is coming with the idea that, for example, in this case, you have a query that is select from sales where product 30 and store CK3, right? A regular SQL query, you need to interpret which is the query that you, or which is the purpose of your query, and finally generate a code that need the abstraction that interpreted generate an overhead, and it will be efficient if not need to read literally the query that you're trying to do. In this case, the query compilation directly generate the code instead of or try to interpret the query of the SQL. Okay, so in this case, for example, under the hood of this query, definitely it will be the code, the algorithmic code to get the data. But if you compare with a regular interpreted and overhead per row, you will see that first you need to define which operator there is in this query, and if we're trying to there is an operation with some column, first trying to validate if the column is an integer and what is a comparison, right? So that's actually generating a compute process that is not efficient when you are trying to do a complex query. So for that reason, a query compilation is better, and is coming with the Git compiler, right? And the next approach that maybe we can use to improve the query engine is coming with vectorized processing. And in this case, is something very different. And the idea is that we have to start with the same query. In this case, product with the same query. So, but the difference is that the vectorized processing will work with bitmaps. So in this case, if you already know that you need two columns, right? You need to only generate a bitmap of each column. In parallel, actually, this vectorized processing can handle large batch of columns at the same time, and then can merge them, right, all them, to finally to get which bitmaps matches and get the rows that finally matches in these bitmaps. For example, in this case, we can see that we have two lists that need to be generate this match, and in this step 3 we can see that these rows matched with my query, and then it can return the answer. With these algorithms, could be efficient than if you use a regular query in SQL. Okay, that's all for now. Thank you for watching this video. Obviously, if you need more details, you can read the book. But well, I will see you in the next time. Thank you.